this talk will be given by two speakers, Dr. Alon, who is the Assistant Professor of Radiology from New York University, and Dr. Kai Tobias Block, Associate Professor at NYU as well. So both are researchers at NYU Center for Biomedical Imaging. Newell graduated from NYU's Biomedical Imaging and Technology PhD program in 2014, and is now an assistant professor working on RF hardware design and development of imaging method based on ultra-wideband microwaves. Tobias graduated from University of Göttingen, Germany in physics. After working at Siemens MR for several years, he joined NYU in 2011, where he focuses on the development of MRI pulse sequences and open source software for rapid clinical translation. So their talk title is Experience from the MR4ALL Hackathon 2023.
Yeah, thank you very much for the kind introduction, Dan, and thank you very much for the invitation to present about our MRI4ALL Hackathon here at this workshop. We were very happy about this invitation because we think that the theme of the MRI Together workshop aligns very well with our hackathon that we organized in October. And so in the spirit of MRI Together, we decided that we should also give this talk together. So with me here is Leo Alon, and we will go back and forth during the presentation. And we didn't really have much time for planning this, so it might be a little bit chaotic. But anyway, so what we want to do today, and I hope you can see our screen here. What we want to do is we want to give a little recap of this MRI4ALL Hackathon that we organized, where we tried to build a complete MRI scanner in just 4 days. And so we first want to talk a little bit about the background, why we organized this hackathon and what the idea behind this specific format was. We will talk a little bit about the planning activities that went into planning the hackathon. And we'll also discuss the design of the scanner that was built during the hackathon. And then we want to show a few pictures and videos from the hackathon to give you an impression what happened during the hackathon week. And then, and this might be the nerve-wracking part for us, we also want to do a live demo of the scanner and do some scans. And then, of course, in the end, we are available if there are any questions.
So in terms of what we wanted to achieve in this hackathon, so this actually goes back to pre-COVID. Tobias and I met one day around coffee at NYU, and we thought to ourselves, what could we achieve? Basically, if we got together, we didn't have any distractions, no answering emails, and we got a bunch of our colleagues together, and we just hacked along and tried to build a scanner in 1 week. So we kind of planned it to be an internal event at NYU, but COVID hit, and that kind of postponed us. And then what happened was we had the I2I workshop, the Imaging to Innovation workshop in 2013 at NYU. And we thought, oh, this would be a great opportunity to get together, and we can kind of piggyback on this event and also have our hackathon. So basically, we asked ourselves, can we build this scanner in 1 week? And here we're kind of going to show you tidbits of what happens. And of course, we wanted the whole experience to be sort of the result of the experience to be open source, so available to the public. It would not be possible without sort of us approaching this group of super talented individuals: Clarissa Cooley, Jason Stockman from MGH, George Verghese from NYU, Sairang Geethanath from Mount Sinai, Tobias and Vito Cienza, also from NYU, from the 3D printing lab. We all kind of organized, came together and started to sort of prepare for this October deadline that we had. And of course, in order to kind of market the event, we had to create a website. So we sort of registered a domain called MRI4ALL.org. And we had this picture of a phantom in this event, where the idea was to basically image a phantom that is unknown to any of the participants. We were super surprised. So we had 74 applicants. Out of those, because we had limited space and we had to divide the participants across different locations. We had to kind of accept only 52, and those were from 16 institutions, mostly from the from the United States, actually. And of course, in preparation for this hackathon, we a lot of the materials had to be ordered beforehand or fabricated, because we used 3D printers to create the scanner. So we kind of started the design a little bit before, maybe 2 months before. And here on the upper right, we actually had a liquid cooled system, and this is on the upper right corner, you can see that. And then on the bottom right, you can see a couple of students working on cleaning the 3D prints. We had a budget of about 10K for ordering parts. So that was kind of where we started from. We had excellent support from the NYU administration for that. And this is the mystery set phantom. So this is a phantom that's about 10 centimeters in diameter, and where no one knew what was inside.
Yeah, so as Leo mentioned, the scanner was completely designed in the computer using a CAD software. So we used Fusion 360 for this. And therefore, we now have this very detailed computer model, 3D model of the scanner, which was also used for the 3D printing of the individual components. And Vito, who worked on the design of the scanner, he really did a fantastic job, I think. He also just recently made us like a small version of the scanner, which is pretty cool. And yeah, let's take a look at the scanner components for a little bit. So this is how the scanner looks from the outside. The magnet has a length of about 36 centimeters. Then the diameter, the inner diameter of the actual magnet is about 24 centimeter. And then there are multiple inserts pushed into the magnet, so that the inner diameter of the bore here is about 12 centimeter. And we didn't really put the scanner on a scale, but the weight is around 30 kilograms. Now, if we remove these outer plastic parts here and look inside the scanner, you can see that the magnetic field of the scanner is created by an Hallbach array. So this Hallbach array is created by 990 permanent magnets, which are indicated here in this red color. And we used N40UH permanent magnets for this. And these magnets are about ½ an inch long, or like cubed, so around 13 millimeters. And here in this picture, in this photograph, you can see how these magnets look like. This is how they were shipped. And these N40UH magnets were specifically chosen because these magnets are a little bit more resistant toward demagnetization. And so these magnets are held in place using these 3D printed ring formers that you can see here. So these ring formers have cutouts where you can push in the magnets. And so this results in the end in a magnetic field strength of about 0.043 Tesla. Now, if we remove all these plastic parts, you can see the complete array of these 990 magnets. And the location, the exact location of these magnets has been calculated using a software that Leo developed. And basically, the software is based on the MagPilot library to simulate the magnetic field for a specific arrangement of magnets. And then the software uses a numerical optimization procedure to optimize the location of the magnets to get a homogeneous field in the center of the magnet. And so this was used to calculate the exact geometry of this arrangement. And then later, this geometry was transferred into the CAD software for doing the 3D printing. Now, under the magnet are different inserts. So the first insert is, or these inserts are stacked into each other. And the first insert is a cooling system for the gradient coils, because it can happen that these gradient coils heat up. And therefore, we have this liquid-based cooling system, which is connected to an external heat exchanger, basically something that you normally use for cooling a gaming PC. And the idea here is to avoid that the magnet heats up, which might result in a drift of the magnetic field. Whether that's really necessary, we don't know yet, but we put it in there. And then below that, we have the gradient coils for the Z, X, and Y direction. And these gradient coils were simulated and calculated using the CoilGen software that has been developed by University of Freiburg. So this software, you can access it using this link here, was used to calculate these wire patterns. And then holders were 3D printed, which have the wire patterns imprinted, so that it was then possible to kind of glue copper wire into the imprints of these prints. And this is the gradient coil in the Z direction. This is the gradient coil in the Y direction. And then this is the gradient coil in the X direction. Then below the gradient coils, we have, first of all, we have two holders for passive shim magnets. So we have these two holders here, and glued to these holders are a number of shim magnets, which are indicated in green color here. And these magnets here, these are also N40UH magnets with a little bit smaller size, with 3 millimeter size. And the idea of these shim magnets is that this is a mechanism to correct for inaccuracies that occur during the build of the magnet. And so the idea is that the magnet has been built, and then the magnet was mapped using a field mapping approach, and then placements for these shim magnets have been calculated, so then we can kind of compensate and optimize the magnetic field homogeneity. So that's the idea of these two passive shim inserts. And then the last component is the receive coil, transmit and receive coil, the IF coil, which is indicated in blue here. So this is basically a solenoid coil with, I think it's 20 windings, right? And it's basically wound around the object holder here, has been tuned to a frequency of 1.83 megahertz and matched to 50 ohms. And again, like the inner part here is then the object holder where you can place an object inside. So if you look into the scanner from the outside, basically this is what you would see, the object holder here. Yeah, and this is basically the basic design of the scanner. And as mentioned before, the scanner had been designed before the hackathon, and also most of these plastic components had been printed before the hackathon, simply because 3D printing takes time, and it just wouldn't have been possible to print all of this in these very few days. So therefore, we wanted to make sure that at least these components are ready for the hackathon. So these were basically the preparations that happened before the hackathon. And then the hackathon week happened. The hackathon came much faster than we anticipated, but then it started. And this is basically what happened during the hackathon. So we first of all met, or for the first time met on Sunday evening, just for an informal get-together. So we just met in a bar so that the participants could meet each other. And then the actual hackathon started on Monday morning at 9 a.m., where we had a kickoff meeting. And this is a photograph here from this kickoff meeting. And during the kickoff meeting, we also had a naming contest for the scanner. So there were different name suggestions, and we had a voting. And in the end, we decided to call this scanner the Zygmatron Z1 in reference to the word zygmatography, which had been originally proposed by Lauterbur in his first paper about MRI about 50 years ago. So we thought it was kind of funny to pick up this name, zygmatography, again. Yeah, and then after the kickoff meeting, the participants were divided into 4 groups, working on the gradients, working on the magnet, working on the IF coil, and working on software. And basically every day, the schedule was that we always met at 9 a.m. in the morning, had breakfast together, and had a short meeting where we discussed the progress. And then the groups started working individually in these different groups, and also ordered lunch and dinner in these different groups. And then people worked as long as they liked to. And we did this on Monday and Tuesday. Then on Wednesday and Thursday, we had a break because of this eye-to-eye workshop. And that was actually quite useful because that gave us some time to print some additional parts. And then the work continued on Friday, and on Saturday was then the final day where we did the integration and testing of the system. And yeah, because there were so many participants, more than we had originally anticipated, it was not possible to do all the work in one space. We had to work in different locations, which was a little bit unlucky, but luckily these spaces were not that far apart. So the RF team and gradient team worked in our main location in 660 First Avenue, where we have a large RF lab. The software team worked at 30th Street, where we had some empty office space available. And the magnet team worked at 22nd Street, where we have a magnet lab. And this is also where the low field lab. And this is also where the final assembly took place. And this is also where the scanner is today. Yeah.
So in terms of the magnet construction, the pieces were quite large. So we had to use multiple sort of prints. You had to divide the rings into multiple parts. Those were fabricated from polycarbonate. And they were fabricated in a way that, you know, you had holes in each of the rings with a little arrow, so you can, once you could line up all the magnets and sort of adjust their, sort of measure their polarity, and then you could basically take, based on the polarity of the magnet, sort of insert it into the holder in a fairly seamless way. And so here you can see in the middle the single ring being created, and on the right side you can see like kind of a time-lapse video of the magnet being constructed, where each ring kind of screwed into the next ring, so you didn't have any bars or whatnot sort of holding everything together. Upon sort of completion, sort of you can see the magnet and the lower right corner, sort of next to the video. And yeah, so that's what it kind of looks like. Of course, sort of a very invaluable tool for sort of when you design magnets is measuring the magnetic field. And so we gracefully got sort of a loaner Hall probe, sort of a magnetic field probe from Metrolab, exactly. And basically, we designed this 3D sort of motion sort of system that is able to move the Hall effect probe inside the magnetic field. And we wrote the software to sort of map the fields. And upon mapping the field, we estimated the homogeneity to be about 3,600 ppm over a DSV of around 10 centimeter cubed. All of those were controlled, by the way, through sort of open source Python, and was placed on Arduino. Them sort of controlled everything. Similarly, so because Halbach arrays are often inhomogeneous, we sort of devised a couple of different schemes to homogenize the field. One of those schemes was using passive shim. So we wrote software that used genetic algorithms basically to place sort of pieces of these smaller 3mm magnets on holders in space, and the placement of those magnets were basically used to homogenize the field. And here we can see the sort of how the simulation software kind of spit out this array for the passive shims. We had sort of in-house developed software that later exported it into CAD that you could 3D print. And then this, and B, you could see the measured magnetic field before shimming. Then you can see it was the simulated shim field maps. And then D was the field where the field was after placement of the shim magnet. So it's basically the shim magnets and the main magnets together. And we managed to improve the homogeneity by maybe 1,000 or 800 ppm or so. And our more recent versions are actually better than this as well. In terms of the gradient construction, we had the CoilGen software export the design for us for the gradient coil. We printed that on a sort of plastic former, where the grooves were used to place a magnet wire inside those grooves. We used a 15 gauge wire which was placed and glued section by section. And upon completion of these of gluing of the sort of the traces, we put Kapton tape around them. And here you can see the participates with a final version of one of the gradient coils on the bottom right, and the three different gradients X, Y, and Z are sort of shown on the upper right corner. Thereafter, we wanted to be able to map the fields generated by the gradients. So we inserted the gradients into the sort of the form or the holder, and we drove them with 1 amp, and we measured the field across the 3 different axes. And here we can see this scan over a field of view of about 10 centimeters, I believe. Similarly, in terms of RF hardware, we saw sort of the transmit receive solenoid was placed sort of squeezed between the 2 passive shims. And in addition to that, we had we designed a RF amplifier with various custom components. The other sort of field homogenization scheme that we devised was using active shimming. We wanted this to be kind of a little bit of a novel twist on ultra low field. Typically, One of the limitations, as we know, in ultra-low field is the homogenization of the field. And in simulation, we proved to ourselves that actually using active shimming could improve the homogeneity quite a bit. So starting from about 3,000 ppm, you would reduce your homogeneity to maybe 100 or so ppm. So that would allow you to do gradient echo imaging possibly. This is still an area of research, so I'm not going to show further results for this. This is kind of where we're working on that.
Yeah, and then on the next slide, you can see a few pictures from the software team. Of course, software development is not quite as exciting as building a magnet. So we put a picture here of the team having lunch. But actually, like a lot of really exciting stuff has been developed by the software team during the week. And the software team was also the largest team, I think. And basically how we control the scanner is that we are controlling the scanner with a red pitaya board. So the red pitaya board is an FPGA prototyping board that you can just order online, and I think it costs around $600 or something like that. Looks like this. So the red pitaya board has an FPGA as well as a small ARM CPU to control the FPGA. And then you have an RF output and you have an RF input, and you also have connectors for a digital to analog converter, which is used for driving the gradients and creating the gradient waveforms. And then it also has an Ethernet connector. So this board was used to control the components, and there is a little bit of a history of using these red pitaya boards for scanner control or for control of community MRI scanners. And I think the first project where the red pitaya boards were used, this was the Okra project by Thomas Witzel. Then later on, Vlad Neknevitsky developed the Marcos software, which is kind of a successor to the Okra software. And then at the same time, Maxim Zaitsev and his team developed the PulseSec framework. And then a little later, Jason and Lincoln from MGH developed a converter that allows converting PulseSec sequences into a format that the Marcos software can read. That's called Flowcra. And then a little later, Sairam and his team developed PyPulseSec, which is a Python version of PulseSec. And so for the control of our MRI4ALL scanner, we decided to put all these components together, which means we are calculating the sequences with PyPulseSec. Then we are converting them with Flowcra into the Marcos format. And then we're using Marcos for running the sequences on the red pitaya. And what this basically allows us to do is we have a console computer where the user can configure the sequence. And then a PulseSec sequence is generated, converted into Marcos. Marcos is executing the sequence on the red pitaya that is connected to our scanner. And then we get the recorded data back in the NumPy format and can perform the image reconstruction. So that's the basic architecture. And of course, we also wanted to make this easy to use and to provide the user a nice experience. And therefore, we also created a user interface for this software, which looks like this here. You can see a screenshot, which basically looks quite similar to the software that you also know from other commercial MRI scanners. And we're going to demo this in a moment, so I'm not going to talk more about the software. Just a few more words about the architecture behind this interface. So we decided to divide the software into 3 services. We have a UI service, we have an acquisition service, and we have a reconstruction service. And these are relatively independent processes. So the UI service is responsible for allowing the user to register a patient. You can configure a sequence here. And then in the end, you can look also at the images. Then the acquisition service is in charge of calculating the PulseSec sequence and running the sequence on the red pitaya via Marcos. And then the acquired raw data is pushed to the reconstruction service, and the reconstruction service then takes that data, performs the image reconstruction, reconstructs DICOM images, and then these DICOMs are pushed back to the user interface. And so this is a very modular architecture, and these services are relatively independent. And this also allowed us to work on these services in parallel during the hackathon. So we actually divided the software team into 3 subgroups, and they worked on these different services. And this very modular architecture also made it very easy to debug the software. So basically, they only communicate over a folder-based task queue. There's also an IPC mechanism for sending status updates, but it's very easy to debug. And maybe just a few last words about the software. because this is the MRI Together workshop, we wanted to make sure that the whole software is built only using open source components. Everything is open source, and it has all been written using Python. The operating system is Ubuntu 22.04, and then this user interface has been written using PyQt5, and then we used a number of support libraries like PyPalSec, or we used maybe PyDicom for writing the DICOM images. And one final thing I want to mention is that we also created a standardized and very easy to use development environment. This development environment installs automatically in a virtual machine using Vagrant. And it also integrates with Visual Studio for code editing and doing code commits. And we provided this development environment a few days before the hackathon. And therefore, the participants were able to install this already before the hackathon, so that on Monday morning, when we started to work, everybody was really ready to go. And I think this was really important to make sure that we actually get work done during the hackathon and that there's not too much time lost. Yeah, and then came to the scanner integration.
So this was the final day. This was the scanner integration. You can see here on the left here. So this was just before the cooling sort of insert was placed inside the magnet. Then here on the middle, after the cooling was inserted, we kind of had to, the tolerances for the gradient coil were quite slim. So we had to kind of use a little bit of force to kind of shove it inside and make sure it's straight in the isocenter. And then on the right side, we see that this is the insertion of the passive shims and the RF coil into the bore. This is at the end, as the last day, sorry, we also took a group photo, and these were all the participants that got together and are all smiling. And one of the reasons they're smiling is this was before we tried to acquire signals. So and here on the right, we can see sort of this is what the MRI sort of looked like. It's a little bit messier than what we have today, but yeah, at the time, this is what happened. Here you can see people a little bit more sullen, with trying to troubleshoot the scanner. This was people stayed up probably until maybe 2 in the morning, 3 in the morning, trying to troubleshoot things. Things did not work as planned, unfortunately, that last day. However, we got something that we thought was something, but we really were not successful. But then gracefully, Jason Stockman and sort of agreed to come back and continue to troubleshoot the scanner. And thereafter, the next couple of days, we started receiving proper signals, spin echoes. And we thought maybe there was a problem with hidden phantom. We created a more simplistic phantom of, funnily, it was 2 test tubes that actually resembled Lauterberg's experiment, but 50 years later. So, and these were the first sort of images here on the right of sort of the projection of those 2 test tubes. And yeah, so we were very happy. Fast forward, we got together a few more times and we started getting spin echoes. Those spin echoes still have artifacts, there are sort of several things that we are working to troubleshoot, but we're getting them one by one. Sort of we're troubleshooting each issue one by one and starting to get more better images of this phantom. Funnily, the phantom that we created had this sort of letters that said "Together is power," and serendipitously, it's kind of funny because of this MRI Together workshop, it kind of fits quite well.
Yeah, and this is where we're standing right now. So we thought it might be interesting to give a quick live demo of the scanner. So the scanner is now sitting still in this lab on 22nd Street in a shielded room, and we can remotely connect to the console computer and show you how the software looks like and how the experience looks like. So I'm quickly just typing in the password. Basically, if you go to the scanner and start the scanner, you first get to this first screen where you have to register a patient, similar to how it's done on a commercial scanner, where you would type in the patient name, whatever. You can also press this phantom button here to pre-populate the data. But let's type in something like some name here, and then you can start the exam. And then you come to the main page of the software. And again, very similar to software from other vendors. So we have 3 viewers here on the top. On the left side, we have a scan queue, sequence queue, and on the right side, we have elements to configure the sequences. And by pressing this plus button, you can insert a sequence into the scan queue, and we have already a bunch of, some of these are test sequences, but also a bunch of imaging sequences. And just for demonstration purpose, I will just insert for as a start, just a acquisition of a spin echo. So we have this demo sequence called RF spin echo. If you click on this, you can change the parameters and then start the scan. I'm going to run the scan now. And of course, it's only acquiring a spin echo without any gradients. And then you can kind of see the result, the acquired signal plotted here in the viewer. Next example would be maybe to run a spin echo sequence. And again, similar to it's on other commercial softwares, we can edit the parameters here. Let's say we do an echo time of 20 and acquire, let's say, I don't know, 96 echoes or something like that. Scan is running now. And then it's plotting the result here. As you can see, it's a nice T2 decay. It's actually pretty robust. So we can actually acquire quite a large number of echoes and still get a nice signal. Here we go. And what you can also do is, right now it's showing 3 viewers here. You can also switch the user interface to show 1 viewer, so that it's a little easier to see that. And some of you might recognize this here. Basically, this is matplotlib integrated into the user interface. So you have all these options to scroll around, zoom around, whatever. Yeah, typically we use 3 viewers. And then the next step would be to run a spin echo sequence with a gradient enabled. So this would be the 1D spin echo sequence here. I can run this now. Gradient direction would be the X gradient. And it's now, again, basically acquiring 1 spin echo with gradient encoding, so a projection. And you can see the ADC signal here. And on the right side, you can see the FFT of that. So a projection along the X direction of the scanner. And I'm just going to quickly run this also in the other directions. This is now the Y direction. And let's run it in the Z direction. And before saying more about that, I just quickly want to start an imaging scan, because the imaging scan will take about 2 minutes. So we can already have the scan running in the background, and I'll say more about this later. I'm just going to start the imaging scan. So with these scans before, we have acquired now 3 projections in the different directions. And whenever a sequence created a result, you see this icon here with this image. And then if you click on that, you can basically load these results in the different viewers. So in this case, I now loaded the basically the projections in the different directions in the X, Y, and Z direction. So kind of like basic projection imaging. Now the sequence here is running. As you can see, this will take about 2 minutes. But basically, yeah, this is now a 3D spin echo sequence, fast spin echo sequence. Similar to other software products, you can kind of like configure the parameters here. In this case, we are acquiring 16 slices and an echo train length of 16. Base resolution was set to 128. Of course, it's a very low field system. So if you want to get nice images, it takes some time. So this image will definitely be noisy. But yeah, basically similar to how it is with like Siemens scanners or Philips scanners. This is basically the user interface. While the scan is running here, I could show a few other features. So by pressing this button here, you can open the study viewer where you can review previous scans. So yesterday we were scanning a little bit, and I can now select the exam from yesterday and look at the different results. And again, we are able to show spectra, graphs, and plots, but it's also able to show images here. And what is nice here is also that all the parameters, all the sequence parameters, you can always look at that by clicking on this show definition button, which will show basically the JSON that's behind these scans that defines which scan parameters should be used. So this is a quite useful tool. What else do we have here? We have a system status button where you can check the status of the scanner. You could also start and stop the different services if something gets stuck for whatever reason, but luckily it's working pretty robustly. There's a log viewer where you can see the different log outputs from the different services. So if there's a problem with the sequence, you would be able to see that here. And then what else do we have? There's a configuration dialog where you can set up certain things. You can configure DICOM nodes if you want to push DICOM images in the end to a PACS or something like that. So this exists as well. And then I think the scan should be done any second. Here we go. And so the images are loaded here. And as you can see, this is now a pretty noisy and low resolution scan of our MRI, together is Power Phantom. And yeah, basically this is the scan that we have now performed. And in the middle here, what you can see is we are also outputting the case-based data. So for diagnostic purpose, you can then also look at the case-based data here and review that. And yeah, in the software in general, we are keeping all intermediate files. So we're keeping the raw data and we are also keeping the PulseSec files. Yeah, and this is basically how you do a scan. And then at the end of the session, you would basically close the exam and then you get back to the main screen. And yeah, so this is basically where the scanner is currently standing. So it basically works. But of course, you've seen there's still some artifacts that we get. And yeah, this is basically what we are currently working on. We are currently trying to analyze where these artifacts are coming from. We definitely still have problems with RF noise. We also noticed that we have very, very bad quality of power in this building. It's a very old building where the scanner is located, and we get a lot of noise through the power lines. We really haven't looked much into the system capabilities yet, so we really haven't measured the gradient performance much, and there's definitely a lot of work that needs to be done on the sequence side. We also haven't really tested this active shim array that Leo showed. That's definitely something that's on our list. Another technical thing that's on the list is to integrate EMI cancellation, so basically noise cancellation. We have prepared the hardware for that, but we haven't really implemented the algorithms yet. I think this could be very interesting because it would potentially allow using the scanner without an RF shield. And then the other thing that we are trying to do is we have created the software. And there are a number of other community-developed scanners that are based on the Rapid boards. And I think we think that it would be really cool if all these community-developed scanners would use one software platform. So we are thinking of maybe supporting other community scanners with the software as well. And then the last point, we are, of course, already starting to think about whether we should do this experiment again, whether we should do another hackathon. And also to mention this, so all the tools we developed here, everything will be available online in our Git repository. Like the software is already there, but we will also add all the other tools like the 3D printing files and things like that. Yeah, and basically this was our summary of this hackathon. So we were really amazed about what happened during that week and how much like enthusiasm and excitement the participants brought to this event and how hard they worked on this. And yeah, we were not sure if it would be possible to actually put all of that together in 1 week. So basically, this whole open source scanner has been created. I mean, of course, this open source scanner our Sigmatron scanner is more like a toy scanner that will probably not have any clinical applications. But yeah, definitely, I think it has a big value in terms of educational purpose. And the participants also submitted 5 abstracts to ISMRM and are currently also working on a paper that describes all the technical details about how the scanner was created. And as I mentioned, we are releasing everything as open source tools. And our hope is that these tools will be used in the future and will live on beyond the hackathon. And yeah, another thing that we thought was really cool is that it also created a community. So the participants of the hackathon, we are all still in touch using Slack, and we are planning to meet at ISMRM. And also multiple participants have indicated that they would be really interested continuing working on the scanner. And yeah, we thought that's really great. So in summary, it was a really interesting experiment, and it was really cool to see how much can be achieved if we really have time to focus on research and really just do the research part, work on science, which is really what we should be doing as researchers instead of just writing emails and doing administrative things all day. So it was a really interesting experiment. And yeah, we would highly recommend other groups to organize similar events. Yeah, and this is what we wanted to show. If there are any questions, we're happy to take the questions.